Our next speaker will be Suvrath Mahadevan, and he will be speaking to us about infrared spectroscopy with the Habitable-Zone Planet Finder, from planets and stellar activity around M dwarfs to elemental abundances of HWO target stars. Go ahead and take it away when you are ready.
Okay, thanks. Okay, great. Well, thank you, everyone. Everybody can hear me all right? Okay, great. So yeah, I want to talk to you a little bit about an actual planet that really follows on from where Tyler has been telling us. And this was discovered with an instrument that we started building about a decade ago, aptly called the Habitable-Zone Planet Finder, because that's what we wanted to do, find planet in the habitable zone. HPF was designed from the get-go as an infrared machine. It was really one of the first of the infrared radio velocity spectrometers. Targeted really for M dwarfs, because the spectral flux of the M dwarfs really peaks in the infrared, specifically kind of mid to late M dwarfs, which are very hard to do in the optical otherwise. It's on the 10-meter Hobby telescope, and it was one of the first infrared spectrometers to really show that we can get to about 1 meter per second, even in the infrared, with these technological challenges of these infrared arrays and things like that. Okay. The science case was very clear from the get-go, really going after habitable zones around M dwarfs. But of course, you're talking about a mass range here of like 6 or 7. So an M0 to a late M is really a factor of 7 or 8. So the habitable zone moves inward, which means that the signal that you get from your planet really is about 10 times what it would be for an Earth around the sun. And even today, for the optical spectrometers, 10 centimeters per second, a signature of the Earth, which is really about 9 centimeters per second, is a little beyond reach. Partly because the instruments are only getting there now, partly largely because of stellar activity. But around an M dwarf, especially a mid-M, you're really talking about 1 meter or 2. So suddenly these worlds now feel like they should be within reach. And that's why we build HPF, to actually find these worlds. It's not enough to just be in the infrared. The M dwarfs are just dim. So you also have to have a large collecting aperture, and we're on the 10-meter Hobby telescope in West Texas. So HPF actually exploits this very large collecting aperture and the Q scheduling of the Hobby telescope. So HPF really was the precursor for another spectrometer that lives not far from here called NUID, which I hope many of you who will go to Kitt Peak will see. In fact, if you see it, I'll be a little worried, because it should be living inside its temperature-controlled room. So you'll really see the room it lives in. But if you actually see it, let me know something has gone wrong. But NUID really does try to push towards these 20 centimeter, 10 centimeter per second limits, really going after, or at least charting the path towards true Earth analogs, whereas HPF really is much more focused on M dwarfs. It's not always the instruments anymore, it's the stars. The stars, the technical term is suck. Stellar activity. Stellar activity is the bane of all radio velocity planet discovery. It's actually kind of awesome, right? One person's signal is another person's noise. But here is an image of the sun in calcium HK and H alpha. And you can see this is not the nice light source that you would want to try to push towards these 10 centimeters or 5 centimeters precision. There's pulsations, oscillations, flares, stellar activity cycles, spots, faculae, all of which are evolving on various time scales. And this is what we're up against when we're trying to find these teeny tiny signals of terrestrial planets. So this is the star I'm going to talk about today, Gliese 251. It is the 74th closest star to the sun, and it's only about a little over 5 parsecs away. A planet was already known around Gliese 251. There was a planet at a 14-day orbit that our Carmenes colleagues had discovered. It's relatively bright for an M dwarf. It's about 9th magnitude or 10th magnitude in V, fairly bright in J. This is kind of as good as it gets for many M dwarfs, right? But we were following this up with HPF when we started seeing a signature pop up around 54 days. This signature was there in the infrared instruments. We would see it in HPF, we saw it in Spiru, but we did not see it in the Carmenes data. So you get pretty suspicious at that point, and you go, wait a minute, is something wrong with our data set? Or is the lower activity that the infrared spectrometers are picking up, because the activity is low, a little lower in the infrared, allowing you to detect another planet that the optical spectrometers are not able to detect? So we kind of leaned into this system with the HPF survey. And just pounded away on it both with HPF and with NUID, which actually does quite well for an M3. M3 is sort of a pretty good spot for both HPF and NUID. NUID is of this instrument set the most precise, followed by HPF. And 20 years of radial velocity observations, probably about 700 RV observations, plus chromatic Gaussian processes later, we have a signal. We have Gliese 251c, which is about 54 days. It's about 3.88 Earth masses M Sinai, always M Sinai with radial velocities. We know the inner planet is not transiting. We don't actually know that the outer planet is not transiting, but likely it is not transiting. Very, very subtle signature, just 1.2 meters per second. What makes this really interesting to us is bang in the middle of the habitable zone, right? And if you look at what stars are imageable, Gliese 251c and Proxima Centauri, Proxima Cent B, are really our best hope for direct imaging with the next generation of 30-meter telescopes. So the ELTs really are going to be able to potentially get an image of these things. But not any ELT, because guess what? You need an ELT in the northern hemisphere for this one. Something we often forget, right? There are two hemispheres, so you can't put all your 30-meter telescopes in the same hemisphere, which is kind of the point of the US ELT program, full sky coverage, because your high priority targets may not just be in the southern hemisphere. This one, which is the second one after Proxima B, just happens to be at plus 33 deck, very hard to access from Chile, right? So 35 milliarc second separation. We don't fully know whether it's imageable with TMT or not. It depends on the exact properties of the imagers that we build, but we're kind of very hopeful. So here we are. We have a habitable zone planet, very exciting, one of the first HZ planet discoveries coming out of the HPF survey. But we also know that HWO is flying soon. And it's time to start thinking about what we might need for those target lists. And the use case I illustrated was using HPF really as a velocimeter, but it's also a spectrometer, right? So you can actually do spectroscopy with it. And we decided to look at phosphorus, which is an element, it's a Chernobyl element, which is very poorly measured because there are no visible lines. There's an ultraviolet set of lines which are hard to get to, but there are just no lines in the visible. But phosphorus, we also know, is pretty critical for biology for many, many reasons that I can get into later. But here we are. There's a beautiful phosphorus line in the HPF bandpass. It's only 4% deep, but this is a 10-meter telescope, and the HWO targets are bright targets. So getting signal to noises of 500-600 on this is not a challenge in a few minutes. So we're actually measuring right now. One of my undergraduate students, Olivier Myers, is measuring phosphorus abundances for a whole bunch of HWO target stars as we speak. Parallelly, Penn State geoscience grad student Adam Stone has just put out a very interesting paper where he shows that depending on the amount of calcium available on a pelagic planet, basically a water world, you have very different outcomes on whether phosphorus is available in the water or not. So generally speaking, phosphorus is available because of weathering, but in an ocean-covered world, you really have to rely on the submarine weathering. And there it turns out that the availability of calcium really drives a lot of the availability of the phosphorus. So when we learned this was very interesting because we said, aha, we have measured the phosphorus, and we can just look up the literature values of calcium. And you can actually make plots like this now about the HWO sample. This is actually for the HWO sample, and this is definitely a do not take a picture plot. It's just an illustrative plot, but I think we're excited about this. There's definitely things here where we can say, if this was a water world, you could have problems with phosphorus availability biotically. So this kind of stuff is very interesting because we can say reasonable quantitative things about the stellar abundances today. Of course, there are questions about how does phosphorus and calcium actually make it into the planet itself, how available they are in the mantle and the crust. We know those issues, but it's great that we're actually able to make real quantitative measurements on the stars now to sort of begin to attack these questions. So in summary, really the infrared spectroscopy is really paying off. New habitable zone planets are being discovered. Indeed, the ELTs, LIFE, HWO are going to be able to really do transformative work here. And we are going to complete the phosphorus abundances for the HWO target stars. Thank you.
Questions for our speaker, and if I can have the next speaker up as well.
Awesome talk. Do you know if there's any plans for GJ251C to be observed by JWST, or if that's already happened and what the status of that is?
One more quick question.
Hi, great talk. Could you maybe speak to the pros and cons of doing your radial velocity measurements in visible versus near infrared, and why, say, we don't do it in ultraviolet or far infrared?
Generally speaking, you want to be where the information is. And the information is a combination of the line density and the stellar flux. So for a G star, an F star, or even a K star, the visible is great because you have a high line density. So you go all the way down to about 400 nanometers, and you can go up to like 600 or 700 nanometers. That's where the information is. With the mid-M dwarfs and later, the information kind of shifts towards the infrared because the fluxes are shifting. There's still a lot of line density in the visible, but there's almost no photons in the star. The ultraviolet has a high line density, but poses a challenge that you are highly susceptible to stellar activity. Whereas in the infrared, it's the opposite. You're almost 2 times less susceptible to stellar activity compared to the optical. So most searches have fixated kind of on the optical end.
All right, let's thank our speaker.